Welcome back to Sholey Physics. In this episode, we're going to be looking at electric field calculations again. And later on, we're going to get into the field calculations for rings. So I'm going to do a half ring and a full ring, just to sort of different some different orientations for those. But this is our part 2 of the series. In this one, I'm going to revisit our line of charge and just thinking about how we put together this electric field calculation. Like, what is dq, what is r in each case? And that's kind of what's going to help you come up with a method, just a way to approach each one of these as you go and solve them. Hope to clear some things up from our part 1 and just bring that out, give you a method in which to approach each of these problems. So thinking about back to the line of charge, I'm not going to go into the specifics of calculating it, but we did have some dimensions here. We're looking for the electric field at this point. There were the length of the rod was 2a, and we're at a position x. And we had to define a little point dq where we had some charge. So there's the dq. Like, what is that? And then when you go plug in dq into this expression to integrate it eventually, what do you replace that with? And also, what is this r value? Also, consider what direction is important. Is there symmetry in certain directions in which this electric field cancels, and which direction, x or y, would the field not cancel? Which one would be significant? We'd have to add it up and sum up that electric field. So that's kind of our steps here. We're going to first think about what is dq. This is our method of solving. What is dq? All right, so we're going to have to figure out what is dq in this case. And number 2, what would that r be? Now I've got r naught because there can be a lot of r's in these cases, especially when we get into rings where there's a radius of the ring, and later on we're going to get to a sheet of charge and there's a radius of that sheet. We're going to have a circular sheet. So I'm just going to say r naught, meaning that r between the distance between the electric field and the dq. That's what we're defining as r naught. Whereas the there may be other arbitrary r's like radiuses in those cases. And whenever you do that, you do need to also think about the other dimensions. We've got a distance to the electric field from that wire, and we also defined a distance y from our little 0 point on this line of charge, or this rod, up to the point dq. All right. So what is dq? What is r naught? And then think about, is the sum of the electric field in the y direction equal to 0 due to symmetry, or is it the x direction, okay, due to symmetry? So do you have some crisscrossing electric field lines? So for example, if there's a little piece of charge dq on this line, and there's a contribution to the overall electric field at this point x called dE. Well, that dE would really be in that direction. There's the dE. All right, so is there a symmetric point from our 0? So if we measure that distance y, if we measure the same distance y down here, is there another dq contributing some of that electric field in that direction where the y components cancel? It might have a y component up there, a y component down there, and those would cancel out. So in that case, the electric field in y direction cancels, and it would only be the x direction components that would be the important pieces. So if we define a little angle theta in there, that would be the cosine component of the electric field. So that's just an important step to consider. And finally, when you set it up, put it together, set up the electric field in that direction where it's important. So in this case, is it x or y? We may even have some kind of z direction in. If you think about like a sheet of charge, we're working out in the outward direction from the sheet. So there might be a different direction there. So set up the equation for solving that electric field, that overall electric field. And that would involve rewriting this and substituting in the dq. So I'll kind of show you how this would work. I'm not going to go through the solution of the line, but this is going to feed into figuring out these rings of charge. And this method is going to be very helpful. So what is dq? What is r naught? Is there any symmetry that we can ignore certain components of the electric field? And finally, we're going to set it up and put it into a form where we can solve it, which includes, I should put in here, includes that vector direction. So it includes the direction. Shelley could stand to write a bit better. That includes direction. I'll just audibly put that up there. All right. So here we go. Step 1, what is dq? Well, this dq is related to the overall charge q. So if this whole rod had a positive charge q, remember it's a rod, it's in a line, so it's a line of charge, it's evenly distributed. So there's a linear charge density, and this dq step is where we're relating the charge of the whole thing to its dimensions. So think about the dimensions as a line. This is a line of charge, so we're going to use a linear charge density, which is the total charge divided by the length of the bar. And next, that ratio, the charge density, is the same as the charge density of a small little segment of it. So what is the, I should define a bar length. The length over here is 2a, so I do want to, it's important to put that in there. The length of the whole bar is 2a, so I had to add that in there. So now we get back to this dq. If we're to think about this top dimension, and in its most generic native form, we are just talking about a little amount of charge q. So if we're talking about a small little piece, that becomes our dq. We take the derivative of q, and we get dq. And now in its native form, what is length? What is this little piece here? Well, it's a piece of y. All right, so if it's a small piece of y, then that little piece has a length dy. All right, so again, take the derivative of what this native form, this 2a is referring to the length, it's in the y direction. So it's just a little piece dy. And therefore our dq becomes, dq is equal to q, big Q dy, we multiply it both sides, divided by 2a. Okay, so that's our first step in there. What is dq? And we've defined it. And next, what is r0? R0 over here, that's just the distance between dq and the point where we're trying to determine the electric field. So using the other dimensions, we got an x and a y there. That means the r0 is the square root of x squared plus y squared. That was a little bit easier to determine than dq. Right, so we have those two pieces. Next, we start to think, is there symmetry involved here? Well, I've already considered that with you all. The y components cancel, so I might say the sum of the electric field in the y direction is 0 due to symmetry. But in this particular case, the x direction components are going to be what we're summing up, we're going to be adding together. So they are not equal to 0 there. And that means we need to set up the electric field in the x direction. But we're going to put in this form, d, electric field in the x direction, equals, so that little x component of dE is going to equal 1 over 4 pi epsilon naught. Just copying this expression. But instead of dq, we're going to go ahead and substitute in our dq value, which is q dy divided by 2a. All right, and divided by, I'll go ahead and put it in here, r naught squared. Now r naught is square root of x squared plus y squared, so r naught squared would be just x squared plus y squared. And we're not quite done yet. We need the x component. So let's define a theta. I'm going to define this angle between DE and the horizontal direction there. I'm going to define that as theta. So the component in the x direction would be cosine component, the adjacent side to that theta, to that angle. So this is going to be cosine theta is what we'll have there. I could put that up here. What is cosine theta? What is that component? But once you have the triangle set up, this angle theta is equal to this angle in here. So our cosine of theta is the adjacent side divided by hypotenuse, x squared plus y squared. And that's what sets up your problem. You get it to a form where you're ready to solve, it becomes a math problem instead of physics. We're going to put the physics part away and just solve the math. Q dy, and we've got times cosine theta, we'd have a q x dy divided by 2a, and we'd have this x squared plus y squared, and this cosine, keep in mind, just write it next to it over here so we can see it all together, is x over the square root of x squared plus y squared. So I've already put in applied the x, multiplied that x in for the cosine, and then the denominator down here, we're going to have an x squared plus y squared times the square root of x squared plus y squared. And that's where, in the previous episode, we ended up with x squared plus y squared to the 3/2 power. And there it was. Now you're ready to integrate. We're going to sum up all that electric field on both sides here. And this is where you also do consider what are our bounds in the y direction. If this is 0 and this thing's length 2a, we'd be going from negative a at the bottom to positive a at the top. Right up there. And that would be our bounds. There it becomes a math problem and you can solve. So we're going to take this method now. What is dq? What is RO? Is there any symmetry? And finally, solve for the components that are important. We're going to take that into some new situations involving some rings. This first one is the half ring. So if we have a semicircle, a half circle, and we're looking for the electric field right there at the middle, we're going to first start out thinking about what is dq, what is r naught, and then think about any symmetry, and finally set this up and solve it. So you can see this whole process laid out here. Our dq, what's that going to be? Well, if this whole semicircle has a charge positive q, then let's think about that. It is a line. It is a curved line. So that's what makes this one a little bit different. So you can also go to linear charge density, just like with a straight line, and that's q over the length. But in this length, let's make a little more sense with the situation. What is the length of this thing? Well, it's a half a circle, and the whole length around a circle is the circumference. It's the arc length of the entire circle. So what is the arc length of this circle? Generically, arc length s is equal to the radius times the angle that you're arcing through. So if we arc through this much angle, then s would be defined as that length of the circle. In this case, we're doing the entire half of the circle. So in terms of angle, half of a circle is pi. Now, if we did the full circle, this would be 2 pi, and that's where you get circumference equals 2 pi r. But that's our arc length. So the entire arc length, L, is going to be equal to r times pi. There it is. All right, r is the defined radius of the circle here. Now, what would dq then be? Remember, the density is charge over length. So this little, we consider now a little tiny piece of that overall charge, dq. There's our dq. We've just defined what it looks like. I just had an old person burp. I'm 42. You know, the answer to life, the universe, and everything. Shoot, my birthday's coming up. I'm only going to be the answer to life, the universe, and everything for a little bit longer. But when you turn like 40s, you start getting that old person burp thing. So it's just kind of like gross. Anyway, moving ahead past old person moment. That dq will give a electric field contribution here, dE, looking like that. So when we're considering that dq at that little point, getting a little ahead of myself here. There's the dq. It also has a little segment of arc length ds. Do you see that? So if we're considering the length in its most native form here, it's just s equals r theta. Well, if that is arc length, then what would ds be? Well, ds would be the derivative of both sides. R is a constant, and if we move from this little piece to this little piece, it creates a little tiny angle d theta. So there's a little tiny, with that arc length, there's an associated d theta. R stays the same, but it's theta that's changing to get that little tiny bit of arc length. So there's our ds, is r d theta. Instead of s equals r theta, we're going to have, I'll put it in here, a ds. Ooh, that's the wrong Q. Shelly is off his game. There we go. Be a d little q. So we're going to have a d little q, and instead of ds, it's r d theta. And that's what we're going to be summing up. As we go around the semicircle, we're summing up charge around this half arc. So we're going to have to sum it up as we go from one angle to the other. In the previous example, we were going from the top to the bottom, so we're summing up all those little dy's as we go down the line. Here, we're summing up the little ds's as we go around the arc, and ds's are d theta, so it corresponds to those little bits of angle. And therefore, to compare to our actual dimensions and given values, we're going to have q over r pi, or pi r, equals dq r d theta. Therefore, our dq is q over r pi times r d theta. And we can simplify that a little bit. Some of our r's cancel, a couple of our r's cancel there. And we end up with dq being the big charge q d theta divided by pi. All right. That's usually the biggest step up. I think the quirkiest part about thinking about the geometry of the situation. Next, what is, so number one, what is dq? Number two step, my method, what is r naught? Well, in this case, all of those dq's, how far away are they from the center? R. That one is super easy in this case. It's a constant r. It doesn't change. But we got to consider what that's going to be, and we've considered it. Next, number three. Is there any symmetry here? Well, if I have a little dq spot giving some de down here, a little angle, well, there's also another dq that would give a, likewise, an equal electric field contribution, but in a different direction. And it can have components that cancel, and those two components would be the y components. So just showing there the sum of our electric field in the y direction is going to be 0 due to symmetry. I like that. Okay. But the x components will add up. Okay, so we're going to have to approach those and figure out what that is. So that's where our step 4 comes in. We're going to set this thing up. Our little pieces of electric field will be from the x direction. I'm going to copy 1 over 4 pi epsilon naught. And then our piece of dq, substitute that in. See how once you get to this step, it becomes pretty quick from there, because we've already got dq is the total charge q d theta divided by pi. And now we're going to divide by r naught squared, but r naught squared is just the radius. All of that charge is at the same position, r. All right. Not quite done, because we want the x component, and the x component is going to be this one, and that is adjacent to the theta, so that is cosine of theta. In this case, there's no like x and y to figure out a cosine for, because our integral is going to be in terms of theta. So we can actually leave that, as opposed to before, when we ended up with a cosine over here, our integral is going to be in terms of dy. So we needed to have our theta in terms of the y value over here. So then at that point, the cosine of theta, I had to substitute x over x squared plus y squared to get that y involved in the integration. In this case, we're looking at it, oh, that theta is the same as the, the type of little d theta we're looking at there. So angle is angle. We're done. We don't need to change that cosine theta into anything else. This is going to give us the x component of the electric field. And now we're going to sum up all those little contributions of electric field from all the little dq's. And that's a constant there. I'll go ahead and put my integration sign in right there. Well, what are the bounds going to be? To figure that out, we can't just go with a 0 to pi, even though it is, a semicircle. Because if we did 0 to pi, since we've defined, this is our reference line right here, and this is theta, then 0 to pi would actually be from here over to there. And if we added that up, we'd actually get 0 electric field, because you'd actually be finding the electric field going left and right from a semicircle that looked like this. So you get a 0 electric field. So be careful with your bounds here. Our angle theta over here is the same as this angle here. So this is actually our 0 angle reference point, 0 radians, I should say. So what we really want to do is sum from like a negative pi halves to a positive pi halves. That's how to figure that out. We can go from a negative pi over 2 to a positive pi over 2. All right, and now we've come to a point where the physics is done. We're done looking at the dimensions, and this becomes a math problem. We're sort of, and if you look at the form here, we're in the same place we were before, where this became a math problem for the line of charge. So we are ready to go and solve this. To move forward here, there's actually a lot of constants in here. If I pull them out, we'd have a q up top, and let's see, we'd have d theta cosine theta, so that's going to be our integrand. So divide by 4 pi, and we do have a pi there and a pi there, so we've got 4 pi squared epsilon naught, and r is also a constant. Okay, r stays constant for all of our little bits dq. So that's also constant. And we got a nice, easy looking integral here. Cosine theta, d theta. Okay, and we're going from negative pi halves to positive pi halves. There it is. All right. So the integral of cosine theta, for me, when you get older and you're not in the zone all the time, you forget things like, oh, it's a derivative of sine positive cosine or negative cosine. Likewise, what's the integral? So I always go back, if this ever helps you, if you have a hard time memorizing that little piece, or if you forget it later on, just think about the sine function. Its derivative is the cosine function, because positive cosine. Because look at that slope to begin with. The slope is positive. So the derivative has to be a positive to start, positive cosine. Therefore, if we have cosine and we integrate, we're going to go back to positive sine. So there we go. Shelley's way to remember if there's a positive or negative on that integrating sine or cosine. Integrating cosine, we're going to get a positive sine out of it. And therefore, we're going to end up with a q over 4 pi squared epsilon naught r squared times sine theta. And we're going to evaluate that from our bounds, negative pi halves to positive pi halves. And just by the way, if you notice here, if we just went from 0 to pi, not thinking about that too much, plugging in sine of pi and sine of 0, you'd end up with 0 electric field here. It'd probably give you a clue that you did the wrong thing. Okay, just moved it over to the next screen there. The electric field is now going to be q over 4 pi squared epsilon naught r squared. Always remember all those pieces. And we're going to plug in a sine of pi over 2, which is what? Let's see. Okay, sine looks like this. Okay, so sine of pi over 2 is there, and sine of negative pi over 2 is there. So pi over 2 is 1 minus a negative 1. That's a result of plugging in our balance to the sine theta. And 1 minus a negative 1 is adding 2, or 1 plus 1 is equal to 2. So our overall result for this half ring of charge is 2q divided by 4 pi squared epsilon naught r squared. You can drop 2 there if you want. To simplify, and there it is. That's our half ring of charge electric field. Moving on to the last segment of this presentation, we're going to be looking at a ring of charge. And in this orientation, here's the middle of the ring. This is a circular ring. I have kind of a 3D view here. So this is sort of like the direction coming out towards us and away from us there. And we're looking at a point along the center ring's axis coming out from it. So you could consider a position like, what if x becomes 0, or if we get far away from this ring, what's going to happen there? I'm also going to start this by working through the method. So what is dq going to be? What is r naught going to be? Okay, so let's figure out what these are going to be in this case. All right, dq in this case, we have again a ring, but this is not a half ring; it's a full ring. It'll still start similarly. You can take the total charge q distributed over its length and come up with a lambda. There's a charge per unit length happening here. Now in this case, the length is a full circumference of a circle. So we do have a 2 pi little r. I'm using r as the radius here. In terms of dq, if we look at a little tiny piece of that ring, dq, there it is, be up top there. And then again, we need to look at an arc length as we go around. So if s is the arc length, equals r theta, again, what's the total arc length of a circle? 2 pi is theta times r, and that gives us the total arc length. Well, if we take a little section, a tidbit of this ring called dq, and you look at like the one side of that dq and the other, there is going to be a little tiny d theta in there, small angle change. So by taking ds, we see that this becomes r d theta, and that's what's going to go in over here. Our little ds becomes an r d theta. And now we've got our grounds to figure out dq. dq is equal to, I'll go ahead and put it over here, q times r d theta divided by 2 pi r, and that's going to equal dq. We do have a cancellation of one of those r's there. R divided by r cancels out. So dq is big Q. Let's get away from blue. Big Q times d theta divided by 2 pi. All right. Now, pause here for a second. What theta is this exactly? I quickly touched on it, but I said there's a little piece d theta right in here. So when we're summing up the electric field in a moment, this theta is referring to this circle here, going around that way. It's not this, okay? That's a different angle there. If I'm going to call this one theta, I'm going to have to call this one something different. Maybe I'll call it phi. Phi, phi, whatever you want to call it, okay? In my college classes, it got called phi, P-H-I. So, phi, phi, pho, phon. It's all a bunch of junk. Just call it whatever you want. Potatoes, potatoes, tomatoes, tomatoes. But I'm going to call this angle, as we sum up this dq's all around the circle, all right, that's the theta that I'm defining here. Let's clean a bunch of that stuff up. All right. call that theta. All right, so that's our direction of theta. Had to be real precise about that. Next thing, what is R naught? Now this is the electric field, little piece dE from dQ. So if this is dQ and we're looking at the electric field from that little segment of positive charge up here, that means there's going to be a electric field contribution dE in that direction. All right, and when I put that little dE in there, I should define this angle. I'm going to call that phi. And so that means this angle over here is also going to be phi. And that makes our R equal to the length of this side of the right triangle. So the R over here is going to be the square root of R squared. R naught is what we're solving for here. It's going to be square of R squared plus X squared. There it is. All right. So that's our R naught, the defined R and X. I said earlier on when we talked about the line that there's going to be a bunch of R's involved. So this is kind of where it becomes a little quirky. That's why I defined it R0, like R naught. What is that going to be? That's this length between the position of the electric field and that little piece of charge dQ. All right, we got dQ, we got R naught. Is there any symmetry? Here we can see at the bottom, there's a little dQ that's going to crisscross the electric field with this one, and their Y components will cancel. Now in this situation, we also have a little dQ over here and a dQ over here. And their crisscrossing components will have one kind of going off in the negative Z direction and the positive Z. So those components cancel also. So it would be important to note here for our part 3 of the method that sum of all the electric field in the Y direction is 0, and in what I'm going to call the Z direction, I'm calling this one coming out of the circle X. So our Z directions are also 0 due to symmetry of those charges on all sides. That means we can focus on the X. So let's put it together. D, E in the X direction will equal 1 over 4 pi epsilon naught times dQ. And our dQ is Q d theta, not phi, d theta, divided by 2 pi, divided by R naught squared, which is R squared plus X squared. And now we need the components that are going out this way. So that's going to be the cosine of phi. Cosine phi. Now cosine phi is x over square root of x squared plus r squared. So let's bring this out. 1 over 4 pi epsilon naught. Then we got a q up top. And wait a second, look at this. D theta cosine phi. That's going to indicate that this doesn't change. The angle, this phi angle between the x-axis and the direction it takes to get to each of those q's, as you go around a circle, notice that that angle does not change. It doesn't change at all. In other words, does r ever change? No, the radius doesn't change. Does x ever change? Nope. That means b never changes at all. So this stuff over here, this is actually a constant material also. It's a constant. And when we pull that out, cosine phi is x divided by, so that's adjacent divided by hypotenuse, x over the square root of r squared plus x squared. That's a constant also. I'm pulling that out front. And in addition, there's more constants here. R and X are constants also. Sholly, what are you doing? This is madness. Look at all these constants. And we can simplify them a little bit. But what I'm trying to get to is the only thing that's changing here is the angle. As we sum up this charge going around, d theta is the only thing that's left at the end of this whole thing. And we're going to sum that up from let's say 0 is up, and we're going to add up all the angles we go around in the circle. We're going from 0 to 2 pi. Wow. The integral on this isn't very hard at all. So what I do to one side, I'm going to do the other. Got the integration going on both sides. We're going to sum them up. And there's a whole bunch of constants in here now. Some of this stuff might combine and cancel and things like that, but actually just combine for now. We can combine this term and this term. We get electric field is equal to, let's see, Q X over 4 pi epsilon naught. And then we have another 2 pi in there. I'm going to leave that as 2 pi. We'll see why. And a 1 over square root of r squared plus x, I'm sorry, r squared plus x squared quantity to the 3/2 if I combine that term and this term. Now what's left over here? The integral of d theta is theta. And if we plug in, so this little thing, the integral is just theta, and we're going to evaluate that from 0 to 2 pi. And that's it. So we're going to have a 2 pi minus 0 in there. Okay. And that gives us 2 pi. A couple of those 2 pi's cancel. Bam, bam. And what we're left with is qx divided by 4 pi epsilon naught, very common fellow, times x squared plus r squared. Oh, what did I do? I just replaced. I'm not gonna reverse those. R squared plus x squared to the 3/2 power. There it is. Our solution. All right, so what's going to happen with this? It's kind of like a crazy solution, but what if x is 0? What should the electric field be? Well, if x is 0, that means all these dq's are pointing in towards the center. We should get 0 electric field. But sure enough, look, x is on the top. If x is 0, the electric field has to be 0. Just to make sure nothing goes wrong down here, we'll still have a r squared to the 3/2 is r cubed. So we'll have a non-zero denominator. Always check for that for safety. All right. So electric field is 0 when x is 0. And what happens as x approaches infinity? Well, we'll get farther and farther and farther away from this hoop, and it becomes, from our perspective, smaller and smaller and smaller. It becomes like a point charge. And sure enough, if you look at this, when x becomes much greater than r, then r becomes a very, very small number compared to x. It essentially has no impact because x is going to be so monstrously huge. And so we'd have down here x squared to the 3/2, which is x cubed. And when we take x divided by x cubed, we get an x squared. So this becomes a q over x squared, like a point charge. And we come to the end of our presentation here. That's about it. And I hope this has been helpful.